Okay, so today we'll cover maybe these 4 topics. So the first one is I'll introduce something called strong convexity. So far we have only looked at convexity, and we'll see that if we have a stronger property, a stronger notion of convexity called strong convexity, we can actually get improved rates of convergence. Then we'll study stochastic gradient descent, and then we'll see what are the benefits it provides over standard gradient descent. And then there is a more improved version of stochastic gradient descent called stochastic variance reduced gradient for some special classes of problems. I'll introduce what those special classes of problems are and what this variance reduction means. And then finally, we'll briefly look at importance sampling as a general technique to reduce variance in stochastic gradient descent. Okay. So this is the plan for today. So let me start with strong convexity.
So, Praneeth, can I quickly ask a question from you yesterday? This is Praneeth, online American. Yeah. So, yes. So the question is, for the Nesterov method, the lower bound also can be shown, right? Same lower bound.
That's correct. Like for the class of smooth convex functions, by smooth we mean that gradients are Lipschitz. For that class of functions, we can show that the lower bound is 1 over square root t, which is achieved by Nesterov's accelerated gradient descent. So that algorithm is optimal for that class of functions.
Okay. 1 over square root t or 1 over?
Sorry, 1 over t square. 1 over t square.
1 over t square. 1 over t square. Yeah. Okay. Thank you.
Yeah. Okay. So let's first define strong convexity. So a function f is said to be mu strongly convex if for every x and y we have okay. So compared to convexity, this is the extra term, right? And for convexity, we said just mu is equal to 0. So mu equal to 0 strongly convex just means that it's convex. So this is a stronger or more general notion of convexity, and mu greater than 0 is a stronger property. So if mu is greater than 0 and this inequality is satisfied for every x and y, then the function f is said to be mu strongly convex. Okay. So if you look at an example, so if f of x is given by the linear regression problem, which is half of ax minus b square. So A is a matrix, x is a vector, b is a vector. Then f.
So L smoothness also implies this, right?
Sorry?
L smoothness will imply this, right?
No, L smoothness is
opposite of this, right?
Yeah, so is an upper bound. So it's like a complementary condition.
This is the other one. Sorry, that's an upper bound. Yeah. Okay. Thank you.
Yeah. So if f is this linear regression problem, then f is, we can show so maybe we can also take this as a home problem for the tutorial. So if f is given by this function, then f is actually sigma min of A transpose A strongly convex, where sigma min of A transpose A denotes the smallest eigenvalue, eigenvalue of A transpose A. Okay. A transpose A is a positive definite matrix, so all eigenvalues are positive, greater than or equal to 0, and sigma min of A transpose A is the smallest eigenvalue, which is closest to 0.
Sorry, this was not clear. And so you're saying if f is this, then f is sigma mean of so what does sigma mean?
Parameter. So I'm saying f is some mu strongly convex for some parameter mu.
Okay.
I'm saying that parameter mu is equal to the minimum eigenvalue of A transpose A.
Oh, okay.
Where A is defined in this function.
Okay.
Okay, so I'm just giving an example to motivate why these mu strongly convex functions are maybe even interesting to study, because even for quadratic functions, we can so for example, if A is non-singular, then sigma then the corresponding linear regression problem is indeed strongly convex with this kind of strong convexity parameter. Okay.
But you need mu to be strictly positive, so non-singularity is important, right?
Yeah. So mu equal to 0 is just convex.
Usual convexity.
Usual convexity, and whatever we did yesterday will apply. When we have mu strong convexity for mu strictly greater than 0, we'll be able to get improved results that we'll see in a little bit. Okay.
So this for the quadratic function, will it be both at the same time mu strongly convex and L smooth? Is it like the borderline case?
Yeah. So for example, here you'll also have L smoothness. So F is the operator norm of A transpose A. Smooth.
So that's like a borderline case, I guess, right? It has.
So there can be, so roughly what strong convexity means is that the Hessian is lower bounded by mu times identity in the Ph.D. sense. And smoothness means that the Hessian is upper bounded by L times identity in a Ph.D. sense. So
does it mean that this becomes equality in this case? Basically, that
it's not equality because the parameters are different. So this is the smallest eigenvalue and this is the largest eigenvalue.
Okay.
Yeah. So this will be like the border case will be when A is identity, when both the smallest and the largest eigenvalues are the same.
Okay.
And the parameter that will be important in terms of convergence rates and so on is the ratio that we have here, which is a smoothness parameter divided. So smoothness is always greater than or equal to the strong convexity parameter, right? And so should we prove that? So maybe that can also be taken as a simple exercise. So if F is L smooth, and mu strongly convex, then L is always greater than or equal to mu. And condition number of a function is defined as, so it's denoted by kappa, is just the ratio of L divided by mu. And this is always greater than or equal to 1.
So what are other examples of such functions, which are both?
I mean, so as I mentioned, right, so the general condition you need is that strong convexity means that and smoothness so any function which satisfies the Hessian, like upper and lower bounds on the Hessian, will satisfy both strong convexity and smoothness. And many times you can think of like, so even if you had a polynomial, convex polynomial, let's say, right? And if you restrict it to a particular domain, so if you think of the entire space, then maybe the smoothness parameter and the strong convexity parameter might grow very large when things go to infinity. But in a bounded domain, say convex polynomials and so on, so you can construct convex polynomials which have bounded strong convexity and smoothness parameters.
Yeah, okay, thank you.
Yeah. Okay, and from yesterday, let's recall one thing which we'll be using maybe multiple times today. if F is L smooth, then okay. So the norm at any point, the norm square at any point is upper bounded by 4L times f of x minus f of x star. So the proof, again, let's just recall for simplicity. So f of x star, because it is the minimum, is less than or equal to f of x minus 1 over 2L grad f of x. And by smoothness, this is less than or equal to f of x minus 1 over 2L let me be more. Actually, maybe I don't need this. Okay, so this is nothing but f of x okay, so just rearranging this gives us that the norm grad f of x square is 2L times f of x minus f of x star. So this will be using. Okay, so the first thing we want to say is about gradient descent for smooth and strongly convex functions. If f is mu strongly convex and L smooth, then gradient descent with I think maybe let's say 1 over 2L. So is the result clear? The theorem says that if the function f, in addition to being L smooth, it's also mu strongly convex. Then if we use gradient descent with a step size which is somewhat small compared to the smoothness parameter, so eta is less than or equal to 1 over 2L, then the tth iterate t plus 1th iterate xt plus 1 minus x star is at most 1 minus eta mu, maybe t plus 1. So it decreases exponentially fast. So t is coming in the exponent here. Earlier we were only saying 1 over t square kind of rates, but here t is coming in the exponent times norm of x0 minus x star square, right? And this can again be converted into, this also implies that the function values of optimality is small. Is less than or equal to L times L over 2. Okay. And then So here we can again plug this in and we'll get a convergence bound even for the function value. So any question about the theorem and why this is stronger, significantly stronger compared to the results that we have been seeing so far? Okay, so the proof is as follows. We again look at xt plus 1 minus x star square. This is xt minus eta grad f of xt star square
So because this is exponential, even if initial point is very far away from x star, it don't matter.
That's correct. That's correct. Yeah, that's the advantage of. Yeah, that's the benefit of this. Like of strong convexity gives us this geometric convergence rate. Like we'll converge exponentially fast. Whereas earlier we were only seeing rates which are more like 1 over t or 1 over t square and so on. So this geometric convergence rate is the key benefit that strong convexity gives us.
Thank you.
Yeah. Okay, so this is just expanding the square. And so on this one, we will use this bound. Okay, and so this is L smoothness. And on this other term, we will use strong convexity. In particular, we will set y is equal to x star and x is equal to xt. Okay. So that would then mean that this is less than or equal to norm of xt minus x star square minus 2 eta times f of xt minus f of x star minus plus 2 eta square L So any questions? So we have just used the bound on this norm grad square that we get from here because of smoothness. And on this term, which is inner product of grad f of xt with xt minus x star, we use the bound that we get on this term using this inequality. Okay, just by the definition of mu strong convexity. Yeah, so what we get is that this is less than equal, this is equal to 1 minus eta mu norm xt minus x star square minus 2 eta times okay, I've just collected terms. So xt minus x star square appears in both these places. That's 1 minus eta mu. And then f of xt minus f of x star appears in both these places. And that's minus 2 eta times 1 minus eta. Okay. Because x star is the optimum, this is less than or equal to 0. Sorry, this is greater than or equal to 0. Okay, and then there is a negative term. if eta is less than or equal to this, say 1 over 2L, or even 1 over L is fine here, I guess. Yeah. If eta is less than or equal to 1 over L, this is positive, this is positive, this is positive. So this entire term is negative. So this is less than or equal to 1 minus eta mu minus x star square. So what we have said, shown is that in every iteration, xt plus 1 moves closer to x star by a multiplicative factor of 1 minus eta mu. So if we just expand this all the way till x0, what we get is this 1 minus eta mu to the t plus 1. Okay. And the condition that we have is eta less than or equal to 1 over L. For this to be as small as possible, we want to choose eta to be as large as possible. So the largest is 1 over L. So the best possible convergence rate is 1 minus mu over L to the t, and L over mu we gave a name which is condition number, which is kappa. So this is nothing but 1 minus 1 over kappa to the t. Okay. Yeah, it converges very fast. So in the case kappa is equal to 1, it converges very fast. There is no dependence on the problem. I mean, the problem parameter is very nice and so on. So that's when it is called well conditioned. So a problem is called well conditioned if the condition number is small. So the convergence is very, very fast. A problem is called ill conditioned if the condition number is large, in which case, so if we approximate this, so this can be roughly approximated as e to the minus t divided by kappa. So roughly, in order to see a constant factor reduction, we need kappa number of iterations, right? So when kappa is large, the number of iterations required for a constant factor reduction is kappa. So when kappa is large, this is large, and when kappa is small, this is small. So well-conditioned problems are those when kappa is small, and ill-conditioned are those for which kappa is very large. Yeah, do you have a question?
I mean, how did you set eta equals to 1 by L?
So I'm saying eta can be less than or equal to 1 over L, under that this condition holds. And I want to choose the largest eta so that this is as small as possible.
Okay.
So that's why I just chose eta equal to 1 over
L. Sort of general question. I mean, so this gradient descent, I mean, it's like in the physics problem is particle in some potential which is just damped here, right?
Yeah.
I mean, so what kind of potential causes this exponential?
So in one dimension, I guess it does not matter. So let's say we have multiple dimensions, and in one dimension the potential is like very sharp. In another direction where it's very flat. So in that case, the condition number will be very large. So basically, the Hessian kind of tells us. So Hessian basically tells us the directions in which you can decompose the landscape, and the eigenvalues tell you how sharp the landscape is in each of those directions. If all the directions are kind of equally sharp, then we can choose a single step size, and that works for all the directions. But if the landscape is very sharp in some directions but very flat in other directions, it's as if you want to take larger steps in like the flat directions, but smaller steps in the sharp directions. But then gradient descent uses only one step size in all directions uniformly. So that's why there is this poor behavior when the landscape is not kind of similar in all the directions.
Do you need mu less than or equal to 1 over 2L? 1 over L is good enough. Oh, you have changed it. Okay.
Yeah, I just changed.
Okay.
Yeah.
You basically need mu strictly less than 1 over L, assuming that it's a well-conditioned problem.
Yeah, I mean, we are just ignoring this term. So even if eta equal to 1 over L, this will be just less than or equal to, like this term will be less than or equal to 0. And we are only keeping this term.
Yeah, but that will become 1, right? So that won't help. If eta is equal to 1 over L, like.
So this part does not change.
If mu is equal to L, then that will become 1, right? What will that be? So mu is equal to L, then this will be 0.
Yeah, so I mean, firstly, if mu is equal to L, it means that your covariance matrix is identity, Hessian matrix is identity.
Right.
And this is basically saying that you just take one step, like one, you can, I mean, in that case, this will also be equivalent to the Newton step, because like
Right.
the grad square is identity.
Right. Okay, thanks.
Okay, so let's now go to the stochastic setting. Yeah, so firstly, why? Okay, so before we go there, maybe let me try to fill kind of a table, which is so we have looked at different settings. So one is Lipschitz, let me call it, and this is usually called non-smooth because we did not make a smoothness assumption. Then we had the smooth, and then we had smooth and strongly convex. And then let's say upper bound. And then there is a lower bound. This is for iterative methods under this black box.
So when you say smooth, you mean some L smooth, right? Like Lipschitz, right?
Yeah, so everything will have a parameter associated with it. So this will have a parameter G Lipschitz. This will be L smooth, and this will be L smooth and mu strongly convex. In general, like the only parameter that's important here is kappa, which is the ratio of these two.
Excuse me?
Yeah.
Is it 1 minus eta mu or 1 plus eta mu?
This is 1 minus eta mu.
No, from that expression, it should be 1 plus eta mu.
Sorry?
From that expression, the above the top line.
Yeah. Sorry, this should be, I guess, plus. Yeah, so I think we are just taking this thing to the other side. So we'll have f of xt minus f of x star plus mu over 2 xt minus x star. Thanks for the catch. Yeah, sorry about that. Yeah, this had to be a plus here. Okay, so in terms of upper bound for just Lipschitzness, we saw this G right? So this was the upper bound, and this was achieved by gradient descent. And the lower bound was also matching. All of them will have some constants. I'm not putting constants, but yeah. So the point is for G Lipschitz, we saw that gradient descent is optimal. It gets an upper bound which matches the lower bound. Under more restriction of we have if you look at smooth functions, then yesterday we saw that gradient descent is not optimal, but Nestrov's accelerated gradient gets something like this, where L is the smoothness parameter. And then there is also a lower bound which we did not prove, which basically also gives the same quantity, okay? Which means that Nestrov's accelerated gradient is optimal for the class of L smooth functions. For this, we just saw that the upper bound for gradient descent is something like e to the minus t divided by kappa. Okay, but the lower bound is not this. It turns out to be minus t divided by square root of kappa. Okay, and it turns out that actually Nestrov's accelerated can also be extended to the smooth and strongly convex setting. And that achieves this square root kappa here. Okay. And as you can imagine, like we can make more rows here by taking like different combinations. Now we can just assume Lipschitz and strongly convex. That has a different, like that class of functions has a different upper bound and lower bound compared to any of these. And then we can, so here smoothness was only Lipschitz continuity of the gradient. Then yesterday we also briefly discussed about Lipschitz continuity of the Hessian or Lipschitz continuity of the third derivative, fourth derivative, and so on. For all of them, we know matching upper bounds and lower bounds. The algorithms will become much more complicated. In particular, if we look at the class of functions for which we have Lipschitz continuity of the Hessian, then there exists optimal algorithms which take in both the function value, gradient, and the Hessian. Okay, and then we'll get we know of algorithms which achieve like the optimal bounds under this Oracle model. So broadly, a large part of dimension independent convex optimization has been focused towards understanding what is the fundamental limit of optimization in these various Oracle models. And we looked at some of them in the lecture so far. Any questions?
So in applications, you get all three. What is the most common kind of functions that one like in the optimization?
So for example, like if you say the most popular function would be something like linear regression, which is quadratic minimization. So that would fall in both of these. Okay. Within machine learning, there are what are called, so linear regression comes in when what you put called a mean square loss. So you take a square, so you have a prediction and then you have a ground truth and you measure the disagreement between them and then you take a square, right? So that's when we get these quadratic things, but you can put other kinds of losses. So another popular thing is what is called hinge loss, where you want both of them, you're trying to maybe minimize the L1 distance between both of them, right? Absolute distance between both of them. So those things will end up leading to the non-smooth or Lipschitz continuous things. And strong convexity often arises because you add something called a regularization term to the problem, meaning that even though I want to solve this problem, if the number of data points, meaning that the number of rows of A is much smaller compared to the dimension of X, meaning that this is actually an underdetermined linear system, right? There are many solutions that are possible. You add what is called a regularization, which means that in addition to this, you add a plus lambda over 2 norm, say X square, okay, where lambda is trying to make this a well-posed problem. Like otherwise it was an underdetermined system. By adding this term, it's trying to make it a well-posed problem. So this usually then leads to strongly convex. So this term leads to lambda strongly convex, lambda strong convexity, right? Okay. So this will lead to this strong convex problem. And then there are other kinds of regularization. So you can also, so there is what is called lasso. So which adds something like lambda times 1 norm of X. And 1 norm of X is not a smooth objective. It's non-smooth. But then there are more sophisticated methods which can still get a rate like this, but they go beyond the black box model. So far we could query the Oracle at some point and it will only give me the gradient. But these are like explicit functions that I'm telling you. You can do different things for different parts. And there it turns out you can go beyond this. Yeah. So let's now look at stochastic gradient descent. Okay, so let's again consider maybe, for example, a function that we would commonly encounter in practice, which is of the form. Okay. So X is a vector, so AIs are also vectors, and AI transpose X is just the inner product between AI and X, and BIs are scalars. So we can think of AI, so AI, BI as data that's given to us, and we are trying to fit a line that explains this data. Okay, because we want to find a vector X such that AI transpose X actually gives us a value which is BI. Okay, so this is the linear regression problem. So if you look at the black box oracle model for the full gradient, so the full gradient is given by 1 over n summation I equal to 1 to n AI transpose X minus BI times AI. Okay, so we just have to differentiate this with respect to X, and then this is the full gradient, right? So in order to compute the full gradient, we have to look at each and every data point A1 to AN, and then compute this quantity times AI. Okay, and each of these is so let's say X is in D dimensions. So AIs are also in D dimensions. So the total computation that we need to do is O of ND. Okay. So at every iteration, we have to compute the entire gradient, meaning that we have to do a computation of n times t, and then we'll be able to compute the full gradient. So this is what the black box oracle that we assume has to do, and then it will return us the gradient. And then we do iterations using these gradients, right? And the number of iterations, if we use say Nestrov's accelerated gradient without strong convexity, so that will give us 1 over square root of epsilon, where epsilon is the desired accuracy. Okay, so the total computation time will be n d divided by square root epsilon. Okay, so the question is, if we don't go with this kind of black box model, which has to look at everything in every iteration, because we have the choice of computing only some of them and do in any given iteration. So the idea is, can we do something better or different by computing only gradients of some of the quantities here? Okay, so one way to formalize this is using the notion of stochastic gradient. So given a function f, so grad hat f is called a stochastic gradient. If the expected value, so this is actually a random quantity. This could be, so let me call this. So let's define the stochastic gradient oracle. So yeah, so let's maybe just consider that this is a random quantity, and it's called a stochastic gradient if expected value of grad hat f at any given point x is just equal to the gradient. Okay, and the variance of the stochastic gradient is given by expected value of So given a function f, a random quantity, a random variable or random vector grad hat f is called a stochastic gradient of f at x if expected value of grad hat f of x is exactly equal to the gradient of f at x. Okay, and the variance of a given stochastic gradient is given by is denoted by sigma squared and is the maximum over all x's of the expected value of the norm square of grad hat f of x minus grad f of x. Okay, and in the context of say this function, right, a valid stochastic gradient would be the following. So given an x, grad hat f of x is just ai transpose x minus bi times ai, where I is chosen uniformly between 1 to n. Right? Because if we take the expectation of grad hat f of x, it's exactly equal to the true gradient, which is the average over all these data points. Right? So in this case, this is a natural stochastic gradient that you can think about. Okay. And towards later, I'll when we come to importance sampling, I'll briefly mention another possibility where we have a. So let it be like this. Maybe I'll come to importance sampling towards the end again. Okay, but hopefully, what stochastic gradient means and is in terms of its definition and how we should think about it in practice, hopefully, is clear from this example. Okay, so the
sorry, Praneeth,
yeah.
No, so what did you write? So the stochastic process is so where is the randomness? Where I
is being chosen uniformly at random. So I is the random variable.
Okay.
And grad hat f of x is defined by a transpose x minus bi times ai, where I is a random quantity. Yeah.
Randomized estimate.
Yeah. For the yeah, that's correct.
But its mean is exactly.
That's correct. Yeah. Yeah.
Sometimes people also, instead of choosing a single point, they choose a subset, like mini batches.
Yeah, so that would be called mini batching. Yeah.
Still be a stochastic gradient.
It'll still be a stochastic gradient. So if you choose, so again, there are two variants. One is called with replacement, without replacement, and so on. But in either case, it will be like this. So if you choose, say, I1, I2. So let's say you want to use mini batch to use I1, I2, and then you take an average uniformly at random in 1 to n, and then you take average of these quantities only over I1 and I2. That will also be in expectation equal to the true gradient. But the hope is that they'll have reduced amount of variance. Yeah. Okay. So
this yes.
Yeah.
So this I random, so AIs are fixed
AIs
matrices
are fixed.
basically.
AIs are fixed quantities. AIs and BIs are all fixed. Yeah.
Okay, so just you pick one of them at random, basically, is it?
That's correct.
Okay.
And when we take expectation over that randomness of which one to pick, it's exactly equal to this average, right? Yeah.
Could you give an example of like some real example of this function f?
Which function?
The function fx.
You want a different example or?
Yeah, so this linear regression, what does AI and BI actually represent?
Yeah, so what I'm saying is, okay, so from a very practical point of view, you want to do some prediction, right? So AI would, let's say you want to do temperature prediction for tomorrow. So AI will involve things that you can measure today, maybe today's temperature, yesterday's temperature, and today's humidity and all those things, right? BI will be tomorrow's temperature, right? And you have a data set collected over multiple days, right? And X is the predictor that you want to train, hoping that if you train on all of the past data, and then you make your measurements today, that will give you today's A. And then I take this X that I have learned from like the previous data and then take its inner product. It will give me a prediction for tomorrow's temperature.
So B is
a scalar.
Yeah, so you said like something.
B is say tomorrow's temperature. Okay. That you don't know how to measure today. Something that you want to predict. And AI is something that you can measure today. Yeah. Okay. Yeah. So F is G Lipschitz. And grad hat F. So this is a stochastic estimate, has variance sigma squared. Then, okay, so I have to introduce what stochastic gradient is. So I'll introduce it just now. So stochastic gradient descent with appropriate eta, appropriate step size. Satisfies.
So assumption of convexity is still there, right?
Convexity is still there.
Okay, just making sure. Yeah.
Thanks. Yeah. And SGD is just the following. Okay. So this is basically trying to do gradient descent, but now we don't have exact gradients. So we are using whatever stochastic gradient estimate that we have. So if you take expectation of this entire thing, then this is basically gradient descent, because expected value of xt plus 1 is expected value of xt minus eta times the expected value of this, which is exactly the gradient of f at xt.
And are you taking average after that? Because your theorem is about the average. If at the average value.
So yeah, so this is the suboptimality of the average point. Maybe a few remarks. So firstly, the simplest proof will be for showing for the average iterate. And there are certainly results which show that even like a similar condition can also hold for the last iterate or averaging only the last few and so on. But the proofs are a bit more complicated. As we'll see, like the proof of this claim is kind of very straightforward and follows pretty much the proof that we did for standard Lipschitz convex functions.
But the rate is the same, right? Even if you don't take average.
Yeah, the rate is exactly the same. So if sigma is equal to 0, we will recover like the previous result.
Okay.
Yeah.
Okay.
In the convergence result, shouldn't there be, strictly speaking, shouldn't SGD like converge in infinite time, because like gradient descent, the gradient goes to 0 as we approach the minimum.
Yeah.
The stochastic gradient strictly will not, right? Because it's not really the gradient of the whole function. So it should just kick around somewhere around the minimum without.
Yeah. So usually, so I haven't yet said what the step size is. So if the step size is constant, it will keep moving in a constant ball, right? But here we'll choose a step size which also decays with the time. And it was the same in the non-smooth setting, where if you have something like a V, if you use constant step size, you could just oscillate on either direction of the actual minimum. But in these cases, you actually choose a step size which goes to 0 as well. So the oscillations also become smaller. Yeah. Okay, so we just again look at the same potential function that we were looking at yesterday, which is x3 plus 1 minus x star square. Okay, and this is nothing but norm of x3 minus x star square. Okay. So we can just take expectation of the entire equation. So we'll get minus 2 eta expected value of the inner product. And okay. So the stochastic gradient oracle, the grad hat f of xt, when we take, so if we condition this on xt and we take the conditional expectation of grad hat f of xt conditioned on xt, because we assume that the expectation of this grad hat f of xt is equal to grad f of xt. So
So your conditioning, what is it that you're doing? Sorry.
Yeah, so I was not very careful about one part, which is that when I'm saying the stochastic gradient, grad hat f and so on,
What
in
is
the algorithm,
measurement?
you are seeing x1, x2, x3, and so on, right?
Right.
So there is randomness at every time instant, right? You are querying the oracle at every time instant. And what I'm assuming here is that even if you conditioned on all of the past that the oracle has returned, even then the conditional expectation of grad hat f of xt is still equal to grad f of xt. Okay.
Oh, so even the conditional expectation is equal.
Conditional expectation is like that, yeah. So actually, this will be fine here, for example, because every iteration you will choose I to be uniformly at random afresh, right? So in some sense, like
Right.
the zero mean noise that you are seeing in the stochastic gradient at every iteration is kind of independent of all the things in the past. So there it does not matter, but there are actually situations when you are getting data from time series and so on, where this independence is no longer true. We have to do something different there to break correlations and so on. But in the most standard way that stochastic gradient descent is used, the like in general, this is true that expected value, the conditional expectation of grad hat f of xt, even conditioned on xt, is still equal to the grad f of xt. Okay.
Thank you.
Okay. So this is for bounding this term. So for the second term, we can just use like the Lipschitzness and the variance property. So this is nothing but the norm of so the mean square. And this is less than or equal to, so this by Lipschitz property is less than or equal to g square, and this by the variance property is less than sigma square. So what we get is the following. So rearranging, what we get is that 1 over t Okay, so and if we choose eta to be equal to norm of x0 minus x star Where the slide is? Yeah, and then combine both of these terms. That basically gives us the result on the average suboptimality, and then we can use convexity to get the same bound on the average iterate. Okay, so what we are using is okay. So just to summarize, if we take the same problem, so if we ignore some of the problem dependent parameters for now, but if we look at the same problem, if we did gradient descent, the total computation was of order ND divided by square root epsilon. Okay. In stochastic gradient descent, it was every iteration requires us to compute only one, like process only one example, which, and if AIs are just d-dimensional vectors, then the amount of time for computing one stochastic gradient is only d, right? And then we have 1 over epsilon square number of iterations, although we are currently ignoring this g and sigma, which are also important. But for now, let's just look at the dependence on the dimensions and desired accuracy and so on. Okay. Okay. So in gradient descent, or if the problem was strongly convex, we will have ND log 1 over epsilon. Okay. So here it's more like the dependence on epsilon is very mild because it comes in a logarithmic factor. Here the dependence on epsilon is quite prominent. It's a 1 over epsilon square, right? On the other hand, every iteration here requires ND amount of computation because we need to compute the full gradient. And here we don't need to compute the full gradient. We'll compute only like the stochastic gradient, which is which takes only d amount of time, but the number of iterations is 1 over epsilon square. Okay, so the question that people started asking was, is there a way to kind of combine the benefits of both of them, which means that we don't have to spend like very large number of iterations as in stochastic gradient descent. We want to get this log 1 over epsilon kind of dependence, but at the same time, we don't want to do ND amount of work in every iteration, but still want to have like retain something of this nature where we do only like few number of iterations, a few number of computations in every iteration. Okay. Yeah.
Sorry, so
yeah.
So I thought the rate of convergence in both cases is 1 by square root t, right? The gradient descent and the stochastic gradient.
So this is actually 1 over square root. So convergence rate can be defined either in terms of the t number of iterations, yeah, or epsilon desired accuracy. Okay. So 1 over square root t, yeah, is like 1 over epsilon square. Because if you want epsilon to be equal to 1 over square root t, then t will be 1 over epsilon square.
Okay.
And similarly, 1 over t square is like 1 over square root of epsilon. Right. So this we call a fast rate. This is slower.
This is the computation time, right?
This is the number of iterations.
Yeah. Yes.
So in one case, we are writing, if I give you 2 iterations, what is the final error? Right. In the other case, I am asking, if I give you a target error that I want to reach, what is the number of iterations?
Okay.
So for example, like this corresponds to, so this is equivalent to 1 over t square convergence rate. So 1 over square root epsilon is actually equal to 1 over t square convergence. Whereas what we got there is actually 1 over square root of t. T is a large number. I'm saying, okay. So what this means is that, so here I'm saying, if I give you t iterations of budget, what is the error you can reach to, right? So 1 over square root t, this will be a small number. And what this kind of notation is saying is, if I want to reach a target accuracy of epsilon, then what is the number of iterations? Yeah, it's not equating, it's like equivalent, like they're equivalent ways of saying the same thing. So maybe let me say it this way. So let me do it there. So error after t steps.
So that is xt minus x star, right? The error would be xt minus.
Error would be, usually we measure in functions of optimality, f of xt minus f of x star.
Okay, right, yeah.
Yeah. So there are two ways to measure. So error after t steps, or number of steps required for epsilon error. What I'm saying is, this here being 1 over square root t is kind of the same as, maybe let me not put a symbol, is the same as this. Hopefully this is clear.
Equal to 1, okay, yeah, so that's fine.
Yeah, so I'm using these rates interchangeably, so that's why it may be confusing.
Right, yeah, no, so my question was, I mean, I thought for both gradient descent and SGD, the first thing was still 1 by root t, or no?
For stochastic gradient, it is this.
And for just gradient descent?
Just gradient descent, it's this.
Oh, it was 1 by, okay.
Oh, for only Lipschitz, yeah, you only get this. That's correct.
Okay, but this is,
but in this case, it's actually smooth function.
oh, okay.
The entire thing is a smooth
1
function,
by
1 over t.
Okay.
But okay, so maybe the confusion was that, as I mentioned, that there is no need for me to use only gradient descent.
Okay.
On the overall problem, I could just
Okay.
use Nesterow's accelerated gradient as well.
Okay.
It would have gotten me 1 over t square.
Right, okay.
And if the problem is strongly convex, I'll get a square root condition number kind of dependence here, right? So the point was, there are these, okay, so maybe accelerated. So there are these accelerated methods which can get ND over square root epsilon, right? But require a lot of computation in every iteration, but converge very fast in terms of number of iterations. And then there is this SGD kind of methods which require very little amount of computation in each iteration, but require more number of iterations. So is there a way to kind of get the benefits of both of them, or is there a balance that we can achieve? And so the method that we are going to look at now basically tries to do that, and it's called stochastic variance reduced gradient. Okay, so the main idea behind this is the following observation, that somehow the variance, if we can somehow reduce the variance of this stochastic estimator, then we might actually be closer to gradient descent than stochastic gradient descent, right? So here, for example, even if the function is G-Lipschitz and also smooth, we cannot overcome the square root t rate just because of this variance. Okay, and so the hope is if we can somehow use stochastic gradient estimators with reduced variance, then hopefully we can do better than the vanilla stochastic gradient descent. So the setting that's considered here is the following.
So I have a question. So for SGD, so have people looked at the worst case analysis, etc.? Like that would be large deviation.
Yeah, again, these results are known to be tight. I mean, this result is known to be tight.
Okay. Okay.
Yeah.
Okay.
And the proofs here are actually quite much simpler because for stochastic algorithms, you can directly use, like you naturally construct a stochastic problem and standard estimates using like Kramer-Rao bound and so on. Like standard statistical estimates are sufficient to give you this kind of lower bound. Just because of variance. Yeah. Whereas in like the deterministic settings, we had to do a bit more work. Here, the lower bounds are actually easier.
Okay. Thank you.
Okay. So the function is this. Okay. So the initial gradient stochastic gradient estimator that we had constructed was something like this. Okay. So we pick an I uniformly at random from 1 to n and then compute its gradient. So this was our stochastic gradient estimator. Right. Now, what variance reduction does is that it adds a zero mean quantity to this one so that the variance of the resulting one is smaller. Okay. And the additional term that's added is the following. So we have some x0 that we have.
So you are concentrating on the regression problem now because you're choosing I to be uniform.
Sorry, can you repeat the question?
Sorry, what I'm saying is, are you concentrating on the regression problem only because you're choosing I to be uniform? I mean,
so this is actually general. Fi need not be a regression problem. It could have like any other loss function. So regression will correspond to square loss, but you can have anything else. I mean, this is easy to check. If you take expectation, where I is uniformly at random, it's exactly the same. Yeah. But like the bigger point is that usually in machine learning, we have functions of this form because each Fi will correspond to the loss or the term contributed by one particular data point. So we have n different data points with n different observations, and each data point will have some constraint that it would like to impose on the parameter that we are learning.
Okay.
So yeah. Okay. So firstly, is it clear that this is again a valid stochastic gradient? So when we take an expectation here, this one will again give us grad f of x, right? And this has no randomness. And when we take an expectation over I here, we will again get grad f of x0, okay, by the same principle. So this entire thing is zero mean. Okay. Yeah.
So you broke up into mean and what did you do in the second?
So this is x. So maybe let's say this x0. So we have some reference point x0. Okay, and then to this we are adding this quantity. Okay. And what I'm saying is this quantity is zero mean because the expected value when you take, so firstly by linearity of expectation we take expectation here, and this one is a fixed quantity. It does not have any randomness, and the expectation of this is exactly equal to this.
So the first thing is this stochastic thing.
This was the SGD stochastic gradient that we looked at in the previous, considered in general, right? Now I'm giving you a different stochastic estimator. And that stochastic estimator is the original one plus something like this. Okay. Because this is zero mean, it's still a valid stochastic gradient. Okay. But the point is, the hope is that somehow this can help reduce the variance in the stochastic estimator. which will lead to faster conversion.
And X0 is just the initial point.
X0 for now, yeah, it's just the initial point. Yeah. Yeah, so let's just look at, so what SVRG would do is that it would use this stochastic estimator for the gradient as opposed to the previous one, right? So xt plus 1 is again xt minus grad hat f of xt, eta times grad hat xt. Okay. So if you look at xt plus 1,
So now your del f is just the new one, right? That
yeah,
just,
it's this entire thing.
okay.
Okay. So if you take expectations, so anyway, so we'll just take expectation of this, and when we take expectation of this by the zero mean property of this one, this will again just boil down to f of xt, grad f of xt. Okay. So we'll have minus 2 eta okay, and we take an expectation of this. Okay, so firstly we can break this down into two parts. So that's less than or equal to 2 times expected value of so I'm just using that so I'm just taking this part here, and this part here. So this actually does not have any randomness. And by smoothness, we also know that actually, okay, so before we go, let me first describe the assumptions here, and then we'll be able to also get results without these assumptions, but it'll make the proof simpler for now. So the assumptions are that each Fi is L smooth. So even the average of these functions is also L smooth, and F is mu strongly convex. Okay. So here I'm using the first assumption, each Fi is L smooth. So consequently, even the average is L smooth. And so we saw like towards the beginning of this lecture. So one of the consequences of smoothness was a bound on the norm square of the gradient at any point in terms of the suboptimality of that point. So this we will use to bound this quantity. So now let's consider this quantity. Okay. So we can again add and subtract grad Fi of x star. Okay. And then this again can be upper bounded as 2 times Okay. So the point is we want to, so both of these look very similar except for here we have xt and here we have x0. So we would like to compute bounds on these kind of expectations. So in particular, we want to compute
So essentially, this will be the variance reduction step, like what you are doing now.
Yeah, this is precisely the variance reduction step. So earlier we would not have this grad Fi of x star.
Exactly.
We would only have had grad Fi of xt square, right? Now
Yes.
we are somehow by adding this reference point, we are able to add and subtract this grad Fi of x star, right?
Right.
And then we can look at like the relative variance of grad Fi at xt versus grad Fi of x star.
Okay.
So
Thank you.
this is, yeah. Go ahead. Okay. Okay, and we want to precisely bound this kind of term, right? That's basically what appears here. And in order to bound the variance of this term, so we'll consider this new function, which is ga of x, which is Fi of x minus something, so that x star is the optimum of this function. So we can do that by looking at this kind of thing. Okay. So look at this function ga of x, which is Fi of x minus this linear term, right? So the first observation is that grad gi of x star is equal to 0. So X star is the minimizer of GI. Okay. And because we have added this linear term only, the smoothness of this does not change because like the gradients are all moved by a constant amount, which is grad fi of X star. So GI is also L smooth because Fi is L smooth. Okay. Now we can use this kind of bound on the gradient of this, and that will precisely give us a bound on this kind of quantity. Okay. So the grad GI of X is nothing but grad Fi of X minus grad Fi of X star. So that's this equality. And because GI is also L smooth, norm grad GI of X square is upper bounded by 2L times GI of X minus GI of X star. Right? That's again using the same this kind of thing. So if we take an average over all n, what we get is that 1 over n. So yeah, so the expected value of norm grad Fi of X minus grad Fi of X star square is 1 over n. Okay, and that's less than or equal to 2L divided by n summation I equal to 1 to n GI of X minus GI of X star. Okay, so this expectation is less than or equal to 2L over n, and then we replace GI with its definition Fi of X and so on, right? Okay, and this is nothing but 2L times F of X minus F of X star minus 2L over n grad F of X star. Just and because X star is the optimum, this is actually equal to 0. So this is precisely equal to 2L Okay, so just putting everything back in this expression. Plus eta square times, there were multiple terms. Yeah, 2L f of xt minus f of x star plus 2L. Actually, there may be 4. Okay, so basically, I have used this equation. This equation. This equation. And then putting it together with this equation. Okay, so what this means is the following. So expected value of so the distance between xt plus 1 and x star is smaller than xt minus x star square minus something that depends on the suboptimality of the current point xt, but could increase something which depends on the suboptimality of the initial point because we are using that for doing this variance reduction. Okay, so if the initial point was actually very close to the optimum, then variance reduction works very well, but the initial point need not be close to the optimum. So if you want to use this to again get a bound, so what we'll have to do is to get a bound on f of xt minus f of x star, right? So 1 over t to t minus 1 And by strong convexity, so sorry, there is a T also here. Yeah. Yeah, this is also an expectation. That's correct. Yeah. So roughly what, okay, so again using convexity, we can think of this as, so f of average is again less than equal to this. Okay. So what we are saying is we take the average point, its suboptimality is upper bounded by the average suboptimality of all the points because of convexity, and that in turn is upper bounded by some constant, we'll get to this in a moment, times the suboptimality of the initial point that we started with. Okay. So after we do this for t iterations, this is basically the amount of reduction that we got as a multiplicative factor compared to the suboptimality of the initial point. Okay. If we now choose, yeah, so let me maybe just write. So if we now choose eta to be something very small, which is say 1 over 10 times L, and t to be equal to say L over yeah 30 times mu. So we need to put these things here, but the point is this whole thing will turn out to be less than a constant, strictly less than 1. Okay, and the reason for that is yeah, so we can do the computation. So eta L is like 1 over 10. So I'll erase this part and do the computation here. So eta is 1 over NL. So if we plug that first here, actually maybe it takes slightly, let's take it to be 20, so this will be 6 divided by 20 divided by 1 minus 4 divided by 20. This is 6 over 16. Okay, that's this quantity. And this quantity is 1 over eta mu. 1 minus 4 eta L is 6 over 20 times T is, sorry, maybe this has to be.
This is 16.
Yeah, maybe 60 L over mu. So let's just use. Sorry? This one? Yeah.
The second one that.
This one?
Yeah.
So eta is 1 over 20 L. So L and mu cancel, we get 20 is 12. Yeah. So the sum is still less than so the point is we can choose these say eta to be 1 over 20 L and T to be 60 L over mu, so that this thing is a constant which is strictly less than 19 over 24, right? So what we have at the end is for those choices f of xt minus f of x star is less than or equal to whatever 19 over 24 times f of x0. Actually, this is an average iterate, and then there is also. Okay. Right. Okay. And if we want to then repeat this procedure by setting x0 to be the new x bar, so we compute the x bar t and then we set it as the new x0 and then restart this procedure. Okay, right? So the total amount of, so let's compute what's the total amount of computation, right? Okay, so let me also first give zero code and then we'll do the computation. So the algorithm is the following for S equal to 1 up to some capital S, we'll compute. So we fix x0 here, right? Initially. Okay. And compute and then for t equal to 1, 2, all the way up to 60 L over mu. Pick I at random. And xt plus 1 is xt minus eta grad fi of xt plus eta grad fi of x0 minus eta grad f of x0. And grad f of x0 we don't have to compute because it's already computed once at the beginning of these iterations. And once we do this for these many iterations, we will set the new x0 to be 1 over t xt that we have from here. And then we'll go back here, we'll again compute grad f of x0. So this is the algorithm, right? So we compute the full gradient only once in a while. And we use that to do variance reduction within stochastic gradient descent for a number of iterations. And then we'll go back again and compute the full gradient and then repeat this procedure. So I'll just do the computation of the, compute the total computation effort that this requires and then we'll stop there. Yeah, so the way it will come up is we'll see the convergence rate. So there, for you, as long as the variance is non-zero, we could only get 1 over epsilon square kind of convergence. Here we will see that we can actually get a log 1 over epsilon convergence rate. Yeah. So the variance is actually changing in every iteration, right? And the variance we can see in the bound that we got here. So variance is kind of f of x minus f of x star. So as and when you are getting closer to the optimum, the variance is actually continuously decreasing. There, in some sense, the gradient will not really decrease with the iterations, and so you'll not be able to get fast convergence. Yeah. So we will have to compute this gradient. So in the context of, say, linear regression, this takes d amount of time. So this will take nd amount of time. So in order to get, so every iteration we are getting a constant amount of decrease. So in order to get epsilon accuracy, so we'll set s to be equal to log 1 or epsilon. Right. So the total amount of cost in computing this full gradient, it's also called full batch gradient, is n times d times log 1 over epsilon. Okay. And the additional term is the cost here. So every stochastic gradient requires d, and then this is condition number. Kappa is the condition number. Okay. So there is also an accelerated version of this, right? But if we only, so let's just try to compare this kind of computation with what gradient descent does and what stochastic gradient descent does. So if you look at gradient descent, the amount of time taken for each iteration is, again, we have to compute the full gradient. So that will be n times b. Okay. And then because of the strong convexity of the function, it will be kappa times log 1 over epsilon. So let me actually call this kappa twiddle, because the definition of kappa here is each function has to be L smooth. When we are doing full gradient descent, we only need the smoothness of the average function f. Okay, but it can be shown that so the kappa here is always less than or equal to d times kappa twiddle. Okay, which is the kappa twiddle here. So this one is always faster compared to gradient descent. Okay. So here these things are multiplied, and here so when we are looking at stochastic gradient descent, we had dependence on sigma square Okay, so each iteration requires only d amount of time, and the convergence rate was sigma times norm of x0 minus x star divided by epsilon square, right? So if you look at the values of epsilon for which where epsilon is very small, this has a much slower convergence rate compared to the log 1 over epsilon that we are getting here. So yeah, so in general, like whenever we want to solve problems which are of this fine, so these are called finite sum problems. We have a finite sum where we have the ability to compute the gradient, but we might want to use stochastic gradients for computational benefits. SVRG kind of tries to get the best of both worlds, where you're also getting the fast convergence rates like log 1 or epsilon that are possible only when you use exact gradients. But at the same time, it's not spending time to compute like the entire gradient in each iteration, but rather is doing so only once in a while, and has a good trade-off between both convergence rate as well as the amount of time spent on computing the gradient in each iteration. So yeah, I can stop here. Yeah. Yeah.
Jaikumar, can you use the microphone?
So, I mean, each iteration you pick a different I. I mean, pick I.
Yeah.
So could we have just cycled through them systematically, 1, 2, and?
So actually, even for standard stochastic gradient descent, the cyclic is very hard to analyze, and there are counterexamples where it could be very slow. One practical way people do it is that you randomly permute the objects and then take a cyclic order. And more recently, so this is called sampling with replacement. That one would be sampling without replacement. So more recently, there have been results which show that sampling without replacement gets at least as good as sampling with replacement, or in some cases even better, like towards the closer to the optimum.
And so right now it is uniform distribution. Is there a reason to like skew it in the direction of FI, which is doing better?
Yeah, I don't know about FI which is doing better, but there are important sampling schemes which try to kind of balance out the smoothness parameter. So in the context of linear regression problems here, right? So each FI is of the following form. Okay. So here the smoothness parameter of this function is basically equal to the norm square of AI. And if you have a setting where some AIs are very small, some other AIs are very large, here we are trying to use a global bound on all the FIs, right? So there we would want to somehow balance the probabilities so that you want to depend on the average rather than on the maximum thing. So there we would want to consider importance weighting schemes where I is picked with probability pi, right? And pi is proportional to say norm of AI square. And this will only have a, so here instead of L, we'll have like the average down there.
But the computation time will remain the same except the constant.
Computation time will, so I mean, gradient computation time will remain exactly the same. It's just that you are picking a different distribution over the AIs, so that it will still be unbiased, but the variance will still be reduced a bit.
This variance will be less, so that will help.
Yeah.
What is the, because mini batching also reduces the variance. So how does the convergence of this SVRG compare with mini batching?
Yeah, so the effect of mini batching, it always reduces the variance by 1 over B, where B is the mini batch size. Here, the key part is that the variance is getting progressively reduced as you go closer to optimum. So this effect mini batching cannot give. Mini batching can only give a constant factor reduction depending on how much you are mini batching.
So, I mean, so this is coming back to the physical question. So, I mean, doing all this, we find X star. And then, so how does it, like you talked about the weather thing, right? How does it, I mean, how do you use it now to predict tomorrow's? So we find X star, right, from this.
Yeah, so the way you would use this in machine learning is that I mean, you have historical data of, say, vector, temperature at like 2 days before, whatever, right? Okay, so let's say AI. This is the features you can observe on the ith day, and temperature on day I minus 2, right? And temperature on day I minus 1, and temperature on day I, right? These are the things you can measure, and BI will be temperature on day I plus 1. This is not a vector, I guess. Right.
So AI is a vector, and but now or day I minus 1, I minus 2, and I.
Yeah. These are the three things we can measure today, and BI would be temperature on I plus 1 for tomorrow that we want to predict. Right. So what we will do is we have this for multiple days. So we want to find an X such that it minimizes. So we have for n days, right? Okay, and let's say this gives us some approximate optimizer X hat. We done gradient descent or whatever we do, right? It'll output some X hat, right? Then my prediction for the next day would be so B n plus 1. So for the next day, I'll get data for so I use all of this data to solve this problem, meaning that I'll try to minimize this function, right? And that will give me some vector X hat.
BI is temperature on I plus 1.
I plus 1 day.
Okay, so I don't have BN, I still don't know, right?
Yeah, BN you don't know, which will be for n plus 1, I guess. Yeah.
No, but then
no. I get, okay, so yeah, maybe you can do for n minus 1.
Minus 1.
Like how much ever data you have. Yeah.
So in this example, n will be 3, sorry, right?
N is the number of data points.
So
this is the dimension of the problem. This is how many of the previous things you are using to predict the future. N is the total number of data points.
So number of like the triplets dates.
Yeah, that's correct.
So how to choose the optimizer here? For example, for different optimizers, like you have this gradient descent or the stochastic gradient descent, they will end up with the different points for the predictions.
So for convex functions, usually that's not an issue. Although because of finite samples and the way they're like actually stochastically, they might actually end up in different places. Okay, so the practical answer is that people do what is called cross validation, which is you have some amount of data that you don't use in this minimization. So even though you have for the last 1 year, you don't use all of that for doing the minimization. You use only 9 months of data for doing the minimization. And then whatever you get, you test on 3 months.
So you segment the training data set and you do some operation and check for the other part whether it's following that particular.
Yeah, whether the prediction is good or not.
And then based on that, you proceed.
Yeah, yeah. But for really large models where you really not only care about the accuracy, but actually prediction on individual days, right? In one case, maybe like there could be 2 different classifiers which have similar objective value. One could be predicting very well on some subset of days. Another could be predicting very well on some other subset of days. This problem people have only recently started looking at in terms of like irreproducibility in machine learning models and so on. Yeah.
Okay, so maybe we should stop break for lunch now, and yeah, so we'll meet again at 2 p.m.